All right, section 1.8 continued. We're going to talk again, continue our discussion on inverse functions. The first thing here is to find the inverse of f of x equals x squared. Remember, first thing you want to change it to y. Then you want to switch the x's and y's. Then you want to solve for y. And notice here, when we solve for y, we're going to have to take the square root of both sides. And remember, when you take the square root of both sides here, you got to put a plus or minus on the side that's not squared. So you have plus or minus the square root of x equals y. Now, as I said in the previous section, not all functions have inverses. If you notice, if I were to substitute a value in here for x, say 4, notice you'd get that y equals plus or minus 2, which means you would have the ordered pair 4, 2, and you would also have the ordered pair 4, negative 2. So that means the inverse is not a function. Which means in this case, if the inverse is not a function, that basically there is no inverse. Because in order for the inverse to exist, it needs to be a function on its own. And since when you put numbers in here for x, you get two answers for y, that means that the inverse is not a function. So therefore, this is an example of where the function would not have an inverse. Another way to tell if a function has an inverse or not is to do what's called the horizontal line test. All right, basically, if you go back to the previous function where it says f of x equals x squared, and you graph it, notice this is going to be a parabola. That looks something like that. What the horizontal line test says is if you can draw a horizontal line and it only intersects once, then you know this graph will have an inverse. If it intersects in more than one point, which this does, that means that the function does not have an inverse, because this does not pass the horizontal line test. All right. So now, if we look at this, let's test it out. So let's draw a function here, like this, and then let's draw another one here. We'll draw an absolute value function. And if you notice, when we do the horizontal line test, here it only intersects in one point, so this one has an inverse. Whereas this one, if you notice, it intersects in more than one point, so it does not have an inverse. Now, something else to consider about the graphs of a function and its inverse. Remember, the graphs of the function and its inverse, they will switch the x's and y's. So for example, like one example I gave, if you had a function f of x equals x minus 2, well, to find the inverse, we just switch the x's and y's, and then we solve for y. And notice we get x plus 2 equals y. So that means the inverse is x plus 2. So here's your function, and here's your inverse. Now, if you were to make a table of the first one, of the f of x, you make an xy table. Notice if you put 0, just put 0, 1, and 2 in. So 0 minus 2 is negative 2, 1 minus 2 is negative 1, and 2 minus 2 is 0. Now if we were to do a table for the inverse, now notice if we put the y values in for x, so we put 0, -1, -2, notice that we get the x values for the y here. So we get, if we put 0 in, we get 2. -1, we get 1. -2, we get 0. Notice the in relationship here, the x's and y's have switched. That is what will happen on the graph of an inverse. So notice if I graph f of x, 0, -2, 1, -1, 2, 0. And there's f of x, x minus 2. Then if I graph the inverse, so 0, 2, -1, 1, -2, 0. Notice there's the inverse. Now, something else to keep in mind is that they will also be symmetric with the line y equals x. The line y equals x is right here, goes through the origin. Notice that the graphs symmetrical. Notice the inverse and the function are symmetrical, meaning they're reflections of each other about this line y equals x. If I took this line and flipped it over the y equals x, it would line in the same spot. They're basically a mirror. This line is a mirror of each other. So these are two things that the graphs of a function and its inverse will have. The x's and y's will be switched for the points, and the lines will be symmetric with the y equals x. So if you have this question here, it says you have a segment that goes from -2, -2 to -1, 0, from -1, 0 to 1, 2. So here's f. And it says graph f and use the graph to draw the inverse. So we have f, and remember the inverse, the x's and y's switch. Well, -2, -2, you switch it, you still get the same thing. -1, 0, you switch it, you get 0, -1. So that's where this would be right there. And then 1, 2, you switch it, you get 2, 1. And notice there's your inverse. And that's all you have to do for a problem like that. Finding the inverse of a domain-restricted function. Well, remember, f of x equals x squared plus 1 normally is a parabola, just something like this. And normally that wouldn't have an inverse because notice it wouldn't pass the horizontal line test. But in order to make it have an inverse, what we do is we just look at part of it. We're just going to look at the part where it's x is greater than or equal to 0, which means on this side of the x-axis, which means we're just going to erase this part right here. So that's what we're going to look at when the x is greater than or equal to 0. So notice what it wants us to do is find the inverse. So if we find the inverse by putting in y for f of x, switch the x's and y's, and then solve for y. So we subtract 1, and then take the square root of both sides. Now, normally I would say put a plus or minus there, except remember, we're just looking at when it's positive, so no plus or minus needed. So our inverse is just the square root of x minus 1. And notice here, notice this point here is 0, 1. So if I put 1 in for x, notice I get 0 for y. Notice if I put 2 in for x, I get 1 for y. And notice basically if I put 5 in for x, 5 minus 1 is 4, square root of 4 is 2. So notice the graph will look something like this. So notice how, if I draw the line y equals x, notice how you have a reflection about that line. And that's how you do a problem like that. There's your homework. Any questions, please let me know.